Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are once again going to talk on optical fibers. In our previous session we discovered and discussed a lot, and as promised, here we are again to discuss more. Friends, for the discussion of the topic we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is an eminent professor of physics, and she is teaching in YMCA University, and it's a technical university where students get maximum of the technical knowledge. Friends, as our subject expert Dr. Sonia Bansal is concerned, she is popular among students because she believes that the students to be benefited through her knowledge, and she gives excellent examples due to which her teachings becomes easier to understand. We know that you might have lots of questions regarding the topic. If you feel so that you need to talk to us and ask questions from Dr. Sonia Bansal, then do call us through our toll-free number. Our toll-free number is 1-800-110-430. I repeat, our number is 1-800-110-430. You are requested to call in the last 10 minutes of the lecture only. Now, I would like to welcome our guest, Dr. Sonia Bansal, once again. Hello, ma'am. Welcome to the lecture.
Thank you, Geetika. Dear students, we are talking about the optical fibers. Last time, we have discussed about the optical fiber, how it is constructed, and types of optical fiber. In the optical fiber, we discuss about that it starts from the core, cladding, and then jackets. The refractive index core is different from the cladding, and apart from that, on the basis of refractive index, we divide the optical fiber into two parts. First is the step index and second is the gradient index. After that, we discuss about that what are the properties which are very important to define the optical fiber is the total internal reflection. In the last part, we have discussed all these properties and all the part of the optical fibers. In this optical fiber part 2, we discuss about the some other properties of optical fiber. We start with the fiber optic specification, in which attenuation, where we discuss about the loss of signals, and dispersion, where we talk about the broadening of the signal and how the bandwidth affects because of the dispersion. And then we discuss about the numerical aperture. What is a numerical aperture? Which measures the largest angle of the light that can be accepted into the core. It means a signal which is passed through the optical fiber must be on the basis of the numerical aperture, and then it will come out at the receiver end. Now, one by one, we will define these specification. First, we define the acceptance angle. What are the acceptance angle? The optical fiber will only propagate light that enters into the fiber within the certain cone. Only that light will pass through the optical fiber which is entering in the cone, entering in the core, which is at the certain angle, and that angle is known as the acceptance cone of the fiber or acceptance angle of the fiber. The half angle of the cone is called the acceptance angle, which is represented by the theta I for the incident light which is entering in the core. Here we see in the diagram that this is the air whose refractive index is mu naught, and here we are having the two part of the optical fiber. First is the core, which is having the refractive index mu1, and the cladding which is having the refractive index mu2. Now the light from the air will enter into the optical fiber at an angle theta I, which is the incidence angle, and that is also the acceptance angle in the optical fiber. Now it will move in the optical fiber in this manner. From the Snell's law, we can take how it is going into the fiber, and then how it is reflected into the fiber, which is mu naught sine I is equal to mu1 psi phi. In the next, we know that phi is equal to, from the previous, here we can write it as phi is equal to 90 minus theta, 90 degree minus theta, and then mu naught sine I is equal to mu1 psi. The phi will be replaced by 90 degree minus theta. Now mu naught sine I is equal to mu1. As we know, sine 90 minus theta is equal to cos theta. So we put sine 90 minus theta is equal to cos theta. Now here we have mu naught sine I is equal to mu1. We can write cos theta, as we know that sine square plus cos square theta is equal to 1. So from here we take the cos theta is equal to root of 1 minus sine square theta, where we know that if theta increases, it means the angle of incidence increases, then phi increases and the theta will decreases. Basically theta represent the critical angle and phi is the reflection. Now there is a maximum value of I beyond which the light ray entering the fiber will fall on the core cladding interface at an angle less than theta c. This is the condition for the total internal reflection, where we see that the light maximum value of theta should be less than the angle of theta c. Now such a ray will be refracted into the cladding and it will not propagate. It means we are getting the total internal reflection. This maximum value of I is written as I maximum and is called the acceptance angle of the fiber. Again we repeat that the maximum value of I beyond which the light ray entering the fiber will fall on the core cladding interface. Here we see that the light at an angle I will fall upon the core cladding interface. This is a core cladding interface. Then core cladding interface at an angle less than theta c. It should be less than theta c. Theta c is the critical angle. Now such a ray will refracted into the cladding and will not propagate. This maximum value of I, we will say that I maximum is called the acceptance angle of the fiber and it follows the total internal reflection and the light will pass through the optical fiber. Now we can write mu naught sine I maximum, mu naught because we are talking about the refractive index of incident light in the air, and now this I replaced by the I maximum is equal to mu 1 minus sine square theta c. Now theta replaced by the theta c and root of that. Now when theta is equal to theta c means when the angle is equal to the critical angle, then according to the Snell's law we can write it as mu 1 by mu 2 is equal to sine 90 degree divided by sine theta c. So we can write sine theta c is equal to mu naught by mu 1. Then we can put this value from this in the above equation. We get mu naught is equal to sine maximum is equal to mu 1 root of 1 minus mu 2 divided by mu 1 square. Mu naught sine I maximum, which is equal to root of mu 1 square minus mu 2 square. Mu 1 and mu 2 are the refractive index of the core and cladding. Now, if we are talking about the mu naught is equal to 1 because we are talking about the air. Incident light is entering into the fiber from the medium air. So, mu is naught is equal to 1. So, sine I maximum we can write it as root of mu 1 square minus mu 2 square. This equation gives the relation between the acceptance angle and the refractive indices of the core and the cladding. Mu 1 for the core and mu 2 refractive index for the cladding. Now here we see this is the incidence angle, or we are adding it as a I maximum, so we can call it as a acceptance angle. Then we see that sine I maximum is equal to mu 1 square minus mu 2 square, means we are taking the relation between the acceptance angle and the refractive index of the core and cladding. The cone associated with the angle I maximum is called the acceptance cone. Then numerical aperture. On the basis of I maximum acceptance angle, we can define the numerical aperture. It is a measure of light gathering capacity of the fiber and is defined as the product of sine of the acceptance angle and the refractive index of the medium to which the end faces of the fibers are exposed. Here we see in the equation Na numerical aperture, which is equal to mu naught, means refractive index of the medium to which the end faces of the fiber are exposed, and sine of I maximum. Sine of I maximum means sine of acceptance angle. The product of mu naught and sine I maximum is known as the numerical aperture. Taking mu naught is equal to 1, talking about the air, so we can write Na is equal to sine I maximum, and we know that sine I maximum is equal to root of mu 1 square minus mu 2 square. From here we know that refractive index del mu is equal to mu 1 minus mu 2 divided by mu 1. This is a journal communication system. Here we see that the information sources, then this is a communication system where we have the transmitter, that is a modulator, then this is a transmission medium, this is a receiver, that is a demodulator, and then the signal will reach from information source to the destination. But when we are using the optical fiber, then we have this optical fiber communication system, means from the information source, information is passed through the electrical transmitter, then here we have the optical source, then from optical source it will pass through the optical fiber cable, then from optical fiber cable it go to the receiver side, and here optical detector present, and that again converted this signal into the electrical signal, and then it reached to the destination. Now we are talking about the different features or different properties of the optical fiber, that is the attenuation. Attenuation is basically defined the transmission loss. What is the attenuation? Attenuation or the transmission loss is the loss of optical power as light travels down in the fiber. It means when we are having the loss of the power, optical power, then we have the attenuation. It means decrease in the signal strength along a fiber optics waveguides caused by absorption and scattering is known as the attenuation. It means the signal loss because of the absorption or the scattering of the light. Attenuation is usually expressed in dB by km. Since attenuation is the loss, therefore it is expressed as P out power out is equal to P in 10 power minus alpha L by 10. We know that alpha L is equal to 10 log 10 P in divided by P out, means we can define alpha L, where alpha is the attenuation coefficient of the fiber. This is basically depend upon the P in or power out. Here we also talk about that the loss of the optical power. Next is the V number. What is the V number? This is an important feature of the optical fiber. What is a V number? V number is the number of modes of multi-mode fiber cable, depends on the wavelength of the light. How many modes is available, and it is depend only on the optical on the wavelength of the light, co-diameter and the material composition. It means the number of modes of multi-mode fiber cable depends upon the light wavelength, diameter of the core and the material composition through which we constructed the optical fiber. This can be determined the normalized frequency parameter, that is the V. So we can write V is equal to pi d divided by lambda root of mu 1 square minus mu 2 square is equal to this mu 1 square minus mu 2 square define the numerical aperture. So we can write it as pi d by lambda n a, where d, what is d? D is the fiber core diameter, lambda is the wavelength of light, and Na we know that it is a numerical aperture. For the single mode fiber, we know that V must be less than 2.4, and for the multi-mode fiber, V must be greater than equal to 2.4. So mathematically, the number of modes for a fiber is given by NS L is equal to V square by 2. That is for the step index. That is for the step index, the NSL numerical, the number of modes for the fiber will be defined by V square by 2, and for the gradient index, the number of mode for the fiber is defined by the V square by 4. Now, the most important is the dispersion. Dispersion. Here we see in the diagram first that this is the time and amplitude versus graph, and this is the input signal. Now we see the output signal. There is a loss in the signal. How the pulse shape is changed when it is passed through the dispersive channel. Here we are having a sharp peaks. Here we are having the broadened peak. Now, what is a dispersion? Dispersion is expressed as the pulse spreading in an optical fiber. We see that this is a sharp pulse, and here we are having a spreading of the pulse. As the pulse of light propagate through a fiber, elements such as numerical aperture, core diameter, refractive index profile, wavelength and laser line width cause the pulse to broaden, and these are also the important features to pass the light into the fiber, and these affected when the dispersion takes place, and these also causes the dispersion. This poses a limitation on the overall bandwidth of the fiber, and this dispersion is denoted by the symbol delta T. What is the dispersion effect in the optical fiber? What the dispersion it plays an important role in the optical fiber. We start with the communication. Dispersion is used to describe any process by which any electromagnetic signal propagating in the physical medium is degraded, because the various wave characteristics, that is the frequency of the signal, have different propagation velocities within the physical medium. It means that the electromagnetic signal which is passing from the physical medium may be degraded because of the wave characteristics, in which frequency is one of them, and it will differently propagate in the optical fiber. The dispersion cause that optical pulses to broaden as they travel along a fiber. The overlap between the neighboring pulses creating errors in the receiver output, resulting in the limitation of the information carrying capacity of the fiber. Because of the dispersion, there is a loss of the signal, and that the receiver side we cannot get the exact information. Now here we see that from the diagram, this is a pulse broadening due to the dispersion. Here we see that the separate pulses at time t1. This is the input pulse. This is the distance along the fiber, and this is the pulse shapes and the amplitude, how it is changing. First we start with the input pulses, and that is the time period is the t1. Second is the distinguishable pulses at time t2 greater than t1, means after the some time it will change. Here we see that this pulse now merge to each other. Now as the time is changing, means the time period of second pulse is greater than that of the time period of the first. Now in the third part we see barely the distinguishable pulse at the time t2 is greater than t1 as the distance along the fiber is increasing. Now this is the inter-symbol interfaces, where we are saying that these are the different pulse, separated pulse. Now they are just going to be the one pulse, and these are going to be broadened. Indistinguishable pulse at the time is t4 is greater than t3. As the distance increases, this input pulse changes its shapes and they are getting broadened. because of the dispersion. Now dispersion and bit, now we see here this is the bit interval T1. This is we know that we have the two bits 0 and 1. Now fiber output with no dispersion will takes place here. So we see that for one bit and this is the another bit, and they are separated with the 0 bit, and as the time changes, as the signal is moving into the fiber. Now see here the fiber output with the dispersion. We see that longer bit interval here we are having a shorter bit interval, but here the longer bit interval. Now see here that this signal is broadened for the one, and for another one this is also broadened, and these are also separated by the 0 bit. The higher dispersion, this is the higher dispersion, the longer the bit interval which must be used. To define the dispersion, higher dispersion, the bit interval will be longer. A longer the bit interval means fewer bits can be transmitted per unit of time. A longer bit interval means a lower bit rate to transfer in the optical fiber. If we talk about the conclusion, then we know that the higher the dispersion, the lower the bit rate, means the signal will not go properly outside the receiver. Now, what are the type of the dispersion? The dispersion are defined by the three types. First is the intermodal dispersion, second is the intramodal, that is the chromatic dispersion, then polarization mode dispersion. One by one we will discuss, that is the intermodal dispersion. Different modes propagated at different group of velocities. In the intramodal or the chromatic dispersion, again divided into two parts. First is the material dispersion, second is the waveguide dispersion. In the material dispersion, the index of refraction of the medium changes with the wavelength. As the wavelength changes, refractive index will change. And the waveguide dispersion, where the index changes across the waveguide, means that the different wavelength have the different delays. That is the intermodal or the chromatic dispersion. But in the polarization mode dispersion, if the waveguide is bifringent, if the waveguide is bifringent. What is bifringent? Is a optical property of a material having a refractive index that depends on the polarization and the propagation direction of the light, how light will propagate into the fiber. That is the polarization mode dispersion. Dispersion effect in the optical fiber, how we see from the diagram that first we discuss the intermodal dispersion. This is one of the type of the dispersion in which multi-mode fiber, different modes travel in the different velocity. Here we see light is moving C, B, A, other different lights are moving with the different, because we are talking about the multi-mode. So various light velocity can enter into the fiber, and here we see that the light ray follows a longer path within the fiber than the light ray in the normal, and all these travel with the different, all these light travel with the different velocities. If a pulse is constituted from the different modes, then intermodal dispersion occurs. Modal dispersion is greatest in multi-mode step index fiber. It means this dispersion is more in the multi-mode step index fiber. The more modes, the greater the modal dispersion. If the number of modes are increased, then the modal dispersion will be more. Typical bandwidth of the step index fiber may be as low as 10 megahertz over the 1 kilometer. This is the threshold rate. Now here we see in the diagram that the fiber axis is here, this is the core, this is the cladding, the light is moving with a different velocity inside the step index fiber. And here we see the signal, narrow pearls at the fiber input, but at the output, as all the pearls gather together, then we get the broadened pearls at the fiber output. Now, next part is the intramodal or the chromatic dispersion. What is the intramodal or chromatic dispersion? Which is caused by the fact that single mode glass fibers transmit light at different wavelength at different speed. It means light will be passing through the single mode fiber and with the different wavelengths, and their speeds also different. Now here we are taking the different wavelength and the different speeds. The ratio of the speed of the light in a medium to the speed in a vacuum define the index of refraction or the refractive index of the material. It means here we are talking about the different wavelength and different refractive index. Now see, next is the intramodal or the chromatic dispersion divided into two parts. The first is the material dispersion. Then what is the material dispersion? Where we talk about the intrinsic properties of the material and the glass. This is due to the intrinsic properties of the material and the glass. Glass is the dispersive medium. We can recall from a high school physics that it is the refractive index of the different colors, different refractive index for the different colors. If we define the light is passing through the different refractive index and light is going at the different colors. The different colors wavelengths have the different velocity in the glass. Different colors means different wavelengths light with the different velocities are moving in the optical fiber. A type of dispersion that occurs in the optical fiber due to interaction of various wavelengths with the physical matter in the crystalline structure of the glass. The refractive index of the glass varies according to the wavelength of the optical signal. It means what signal is entering into the glass. Then material dispersion is the phenomena whereby material causes a bundle of light spread out as it propagates into the fiber. Next is the waveguide dispersion. It is also the part of the intermodal chromatic dispersion. In this we have the dispersive nature of the bound medium. In the bound medium, like optical fiber, the velocity is a function of the frequency. It means the velocity will move according to the frequency of the light. The waveguide dispersion is chromatic dispersion which arises from the waveguide effect. The dispersive phase shift for a wave in a waveguide differ from those which the wave would experience in the homogeneous medium. It means medium is changing. It means we are not talking about the homogeneous medium. As the light passing in the homogeneous medium, now here the light is changing, passing in the heterogeneous medium. And the waveguide dispersion is important in the waveguide with the small effective mode area. But the fiber with the large mode area, the waveguide's dispersion is normally negligible and the material dispersion is dominant. It means that it also depends upon the material which are using to construct of the optical fiber. Here we see this is a shorter, this is a longer, and this is the index profile. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us this session. Friends, you are requested to be with us as we are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, as you know that today also we are talking on optical fibers in detail, and for the discussion on the topic we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is an eminent professor of physics, and through her we always try to get in-depth knowledge on various topics, various issues, and we believe that you also try to take maximum benefit through her. Friends, if you have any question pertaining to the topic that is optical fiber, then you can ask questions through our live session. You are requested to call in the last 10 minutes of the lecture through our toll-free number. Our number is 1-800-110-430. I repeat, the number is 1-800-110-430. Now we would like to welcome our guest, Dr. Bansal, once again, and would request her to continue further.
Thank you. Dear students, we are talking about the dispersion, and we are talking about the type of dispersion, in which we discussed about the intermodal dispersion, and then we define the intramodal or the chromatic dispersion, which again divided into two parts, which is the material dispersion and second is the waveguide dispersion, and then the last one is the polarization mode dispersion. Now we discuss about the polarization mode dispersion. What are the polarization mode dispersion? In the polarization mode dispersion, unequal velocity of the two orthogonal state of the polarization is defined. It means the polarization mode dispersion is due to unequal velocities of the two orthogonal states of the polarization. Here we see we are having the initialization polarization state, and these all are having the unequal velocities. Previously we defined having the different velocity, now here we are defining the unequal velocities. Now polarization mode dispersion puts the ultimate restriction on the data rate on the long signal mode optical fiber. The pulse slowly broadened due to the statistical fluctuation of the velocities of the two orthogonal polarization. From here diagram we see that polarization mode dispersion, initialization polarization mode. Now it is varying bifringal along the fiber, and the output is in this form. This is destructive form. Now see that attenuation in the optical fiber, that is the polarization of the mode dispersion. Now next is the optical fiber losses. In the losses we discuss about the attenuation. Attenuation means loss in the signal. That attenuation limits the optical power which can reach the receiver, limiting the operating span of the system. As the light passes from the optical fiber, and the losses will take place, and that is measured by the optical power loss. Once the power of the optical pulse is reduced to a point where the receiver is unable to detect the pulse, then error will occur. Then attenuation is mainly of the result of light absorption, scattering of the light, bending losses. Attenuation is defined as a ratio of the optical input power to the optical output power. The following equations define the signal attenuation as the unit of the length. Previously we have defined it that alpha is equal to, this is the attenuation coefficient, is in the unit of dB by km, is equal to minus 10 by L log of 10 P output and P input, the input power, and this is the output power. Now optical in the types of attenuation, absorption losses. The causes by the fiber itself by the impurities in the fiber such as water and the metals. Then the loss will take place. Then the scattering loss and the bending loss. These two type of loss because of the absorption loss. This is the intrinsic loss mechanism caused by the interaction of the photon with the glass itself. This is the type of attenuation. First is the absorption loss, second is the scattering loss, third is the bending loss. In the absorption loss, this is the because of the impurities in the fiber, which may be the water or the metals or the impurities added into the fibers. Second is the scattering loss. It is intrinsic loss mechanism caused by the interaction of the photons with the glass itself, and the light will be scattered inside the optical fiber. and hindered by the glass. Then bending loss introduced by the physical stress in the fiber. One by one we will define. Material absorption losses is caused by the absorption of the photons within the fiber because of the material. When a material is illuminated, photons can make the valence electron of an atom transition to the higher energy levels. It means the valence electrons, the photons can make the valence electrons of the atom transitions to the higher energy level when the metal is illuminated by the light which is falling into the optical fiber. The photon is destroyed. The radiant energy is transformed into the electric potential energy. This energy can be re-emitted or scattered. Freeze the electrons, that is the photoelectric effect, not in the fibers. Dissipate the rest of material transferred into the heat. In the optical fiber, material absorption is the optical power that is effectively converted to the heat dissipated into the fiber. It means this fiber, this is the material absorption because of the heat dissipation into the fiber. The two types of absorption exist. One is the intrinsic absorption and second is the extrinsic absorption. In the intrinsic absorption, the interaction with one or more components of the glasses, but in the extrinsic absorption, the impurities within the glass. It means when the light photons interact with the one or more component of the glass, that is the intrinsic. When it is interact with the impurities of the glass, then it is the extrinsic absorption. Then material absorption losses, would elaborate it. First is the intrinsic absorption is caused by the basic fiber material properties by which the optical fiber are made. If an optical fiber is absolutely pure with no imperfection or no impurities, then all the absorption will be intrinsic. The intrinsic absorption in the ultraviolet region is called by the electronic absorption bands. Intrinsic absorption occurs when a light particle photon interact with the electron and excite to the higher level. In case of extrinsic absorption, the impurities are added into the material or impurities are attached to the optical fiber, then it causes the extrinsic absorption. Extrinsic absorption is caused by the impurities caused by the which is introduced into the fiber material. The metal impurities such as iron, nickel, chromium are introduced into the fiber during the fabrication. The extrinsic absorption is caused by the electronic transition these metal ions from the one energy level to the another energy level. Here we see that the interaction from the electron and excite to the higher energy level. Here it is takes place in the one energy level to the another energy level, that is the extrinsic absorption. In the optical fiber losses, we define that the fiber band losses. This is another type of losses, another type of attenuation. Then here we define the band losses. Banding means when the optical fiber bends from somewhere. Then bending losses is classified according to the band radius of curvature. On the basis of that, it defined by the 2 point. First is the micro band loss and second is the macro band loss. In the micro band losses, as we see in the diagram, that micro band losses are caused by the small discontinuities or imperfection in the fiber, uneven coating application and improper cabling procedure increases the micro band losses. external forces are also a source of micro bands. Here we see in the diagram that this is external force and this optical fiber. The core part of the optical fiber is band here. This is a micro band. And here we see that external force is applied to the fiber, and then there is a loss in the signal. Next is the macro band losses. In the macro band losses, we observe that when a fiber band's radius of the curvature is large as compared to the fiber diameter. This is the fiber diameter and its radius of curvature is large. These bands are a great source of loss of the signal when the radius of curvature is less than the several centimeters. Here we see the shape of the optical fiber, and in this manner the losses will take place. Here we also see the signal vibration into the optical fiber. Linear scattering losses in the light inside the fiber optics. This is that type of losses in which the light scattering is a form of scattering in which the light is propagating energy is scattered. It means the light scattering can be thought of as a deflection of the ray from a straight path. Here we see the light will be deflected from the straight path. Now the path will be changed. For example, by irregularities in the propagation medium, particles, or in the interface between the two medium. Because of this, the light scattering losses will take place. Linear scattering losses. In the linear scattering losses, with deviation from the law of refraction due to irregularities on the surface are also usually considered to be the form of the scattering. Here the light is losing from the surface because of the irregularities in the surface. When these irregularities are considered to be the random and dense enough that their individual effects average out, this kind of scattering reflection is commonly referred to the diffuse reflection. And the linear scattering may be of the two type. Number one is a Rayleigh scattering and second is Mie scattering. Now Rayleigh scattering, how we define the Rayleigh scattering? Here it is dispersed, or the signal will be lost at the surface. Now here we see the scattering losses are caused by the interaction of light with the density fluctuations within the fiber. As the density changes, it produces optical fiber because of the manufactures. Density changes are produced when the optical fiber are manufactured. During the manufacturing regions of the higher and lower molecular density area relative to the average density of the fiber are created, and the light traveling through the fiber interacts with the density area, then partially scattered in all direction. It means it will travel through the fiber interacting with the density area which may be created at the time of the manufacturing, and then loss will take place. Then in commercial fiber operating 700 nanometer and 1600 nanometer wavelength, the main source of the loss is the Rayleigh scattering, and thus here we define that this is the bunching of the atoms, this is a light loss, this is light loss, this is a Rayleigh loss, and here backscatter of the light will take place into the surface of the core cladding. The Rayleigh scattering is the main loss mechanism between the ultraviolet and the infrared region. It means when we are having the ultraviolet light or infrared light, then Rayleigh scattering takes place. The Rayleigh scattering occurs when the size density fluctuations or the fiber defect is less than 1/10 of the operating wavelength of the light. Then the scattering may take place. As the wavelength increases, the loss caused by the Rayleigh scattering decreases. The wavelength of the light increases, the loss will be minimum. This is the Mie scattering. Mie scattering, if the size of the defect is greater than if the size of the defect is greater than that of the 1/10 of the wavelength of the light, then the scattering mechanism is called the Mie scattering, and this is from the name of Gustav Mie. It is caused by these large defect in the fiber core scatters light out of the fiber core. Here we see the light will be scattered from the fiber core, and this is unevenly distributed. However, in the commercial fibers, the defect of Mie scatterings are insignificant, and optical fiber are manufactured with the less defects, so that light cannot be scattered and the proper signal we will receive at the end side. The linear scattering may also occur in the inhomogeneities, and they are comparable in the size of guided wavelength. This type of scattering is because of fiber imperfections. As what are the causes because of the scattering of the light? Number one is irregularities in the core cladding interface, means the core cladding surface is not smooth or not regular. Number two is the core cladding refractive index differences along the fiber. Sometimes scattering can take place because of the different refractive index of the core and the cladding. And third is the diameter fluctuations of the optical fiber of the core and the cladding. And fourth is the strains and bubbles in the optical fiber at the time of manufactures. Now we start with the scattering intensity, which can be very large if the scattering inhomogeneities size is greater than the 1/10 of the operating wavelength of the light. Such inhomogeneities created the scattering in the forward direction, and that is called the Mie scattering. Now, optical fiber losses we define for the non-linear optical effects. In the optical waveguide do not always behave as linear channel. Sometimes it is behave as a non-linear channel, where the optical output power is equal to the optical input power. Several non-linear effects occurs which causes the scattering. Up to now we discuss about the linear, now we discuss about the non-linear. Means we are having a various non-linear effects and which causes the scattering also. Non-linear scattering is the transfer of optical power from one mode to be transferred in either the forward or backward direction or other modes at different frequencies. It means in this scattering the optical power changes. It may be go towards the backward side, maybe forward direction, or moving with a different frequency, as we are talking about the non-linear optical effects. Types of non-linearity in the optical fiber. First is the stimulated Raman scattering, that is in the non-linear optics. Light propagate in the non-linear optics. Second is the stimulated Brillouin scattering. Third is the self phase modulation. Fourth is the cross phase modulation, and fifth is the four wave mixing. How we will see here that the non-linear effect in the optical fiber divided into two parts. First, non-linear refractive. Second is the inelastic scattering. This non-linear effect loss because of the non-linear refractive, and second is the inelastic scattering. Now this non-linear refractive index effect is defined here by the three methods. First is the SPM, means self phase modulation. Second is the CPM, which is the cross phase modulation, and fourth is the four wave mixing, which is FWM. These all threes comes under the non-linear refractive index effect. Apart from that, these two comes under the inelastic scattering effect, which are SRS, means stimulated Raman scattering, and second is the SBS, means stimulated Boolean scattering. We will define one by one. Here we see that first is the stimulated Raman scattering. We know that the Raman plays a very important role in the scattering. In the stimulated Raman scattering, that is SRS, a high frequency optical photons generated. The stimulated Raman scattering process is initiated by the noise, thermally induced fluctuations in the optical fiber and active vibrational mode. As the incident pump field, omega p is the frequency, interacts with the vibrational fluctuations, losing a photon which is downshifted in the frequency by vibrational frequency omega to produce the stock waves omega s, and also an optical phonon, that is a because of the quantum of vibrational energy. The pump decays with the propagation distance, and both the phonon population and the stock wave grow together in case of the stimulated scattering. Here we see from the diagram that if the generation of the rate of stock light exceeds the loss, then the stimulated emission occurs and the stock beams grows exponentially. The threshold power PR is given by the 5.9 into 10 power minus 2 d square lambda alpha dB. Here we see from this framework that noise fluctuation in optical fiber and molecular vibration. This is the Raman scattering takes place where we have the decay to the thermal bath, that is the heat, and here with the optical phonon vibrational mode, that is a decay in thermal bath, that is also the heat. Now the grow together and the drive each other and it will move. Again we see here that the different frequencies fall upon the normal mode and excited mode, then we have the omega p minus omega s, then it will be come out. Now stimulated Boolean scattering. In this type of scattering we have a high frequency acoustic phonon generation. Here the stimulated Boolean scattering is the modulation of light through thermal molecular vibrations within the fiber. This type of scattering will take place because of the thermal modulation, molecular vibrations. The scattering light appears as upper and lower side bands which are separated from the incident light by the modulation frequency. Both are having the different frequency. The stimulated Boolean scattering is significant above a threshold power density, and that this threshold power density will be defined by this 4.4 into 10 power minus 3 d square lambda square alpha dB and V. We know that d is the fiber core diameter, lambda is the operating wavelength, alpha dB is the fiber attenuation, and V is the source bandwidth. The stimulated Boolean scattering is significant above as a threshold power density, and that will be defined by this value. And similarly here we have that stimulated Boolean noise fluctuation in the optical fiber and the sound wave field Boolean scattering takes place, optical phonon, then this decay to the thermal bath, that is the heat, again decay to the thermal bath, that is the heat, and grow in the opposite direction but still drive each other. Next is the Kerr effect. Kerr effect is due to the non-linear response of the material. It means that the index of silica through which the optical fiber are made is now depending on the optical field propagation through it. The power dependence of the refractive index is responsible for the Kerr effect. Now, depending upon the type of input signal, the Kerr non-linearity has a three different effects, which are: number one is the self phase modulation, that is SPM, cross phase modulation, that is the CPM, and the third is the four wave mixing. Now we define the four wave mixing, where we have the non-linearity in the refractive index is known as the Kerr non-linearity. The non-linearity produces a carrier induced phase modulation of the propagation signal is known as the Kerr effect. We know that n is equal to n plus n2 divided by p by n is defined the ordinary refractive index of the material, n2 define the non-linear index coefficient, p is the output, and a effective define the effective mode area in which the light is propagating. The numerical value of n2 will be taken as, which is a non-linear index coefficient, 2.6 10 power minus 20 meters square per watt, and this is the formula to get the non-linear output. Now, non-linear optical effect due to Kerr effect are defined by the self-phase modulation. Second is the self-phase modulation, in which the intensity modulated signal propagates in the fiber. The intensity modulation induces an index modulation of the fiber, and in return the phase modulation signal will be as we see in the diagram. The signal modulated self, the SPM induced phase modulation broadened the signal spectrum. Here we see there is a blue shift, this is a red shift transmitted signal, and after that, when the self phase modulation takes place, the pulse broadens as it travels down to the fiber, and these are the frequency grips. Now we see that the self phase modulation is the non-linear phase, follows exactly the power shape of the optical pulse. You see in the diagram that this is the input and this is the output when is passed from the self phase modulation. The frequency crisp is the then propagation, the derivative of the optical power. If the pulse propagates under the non-linear regime, then the optical frequency will decrease on the pulse leading edge, and the optical frequency will increase on the optical trailing edge. Here we see that this will be changing. This is the self phase modulation. Thank you.
With this note, thank you so very much for giving us this session. Friends, you are requested to write to us at info.cec@nic.in. We are going to meet again soon. Till then, take care. Goodbye.